So next I would like to introduce Dr. Saampras Ganesan, who has a broad background in biomedical engineering, robotics, neuroimaging, meditation and philosophy. After a Master's in Biomedical Engineering in 2020, he completed his PhD this year, where he used high-resolution functional 7 Tesla MRI to map neural substrates of meditation and evaluate the feasibility of using real-time neurofeedback to support meditation training amongst beginners. As part of his PhD, he led the establishment of the first 7T real-time FMRI neurofeedback facility in Australia, and his research has involved advanced neuroimaging and neurofeedback methods. Saampras also co-founded and co-chairs the Enigma Meditation, a global consortium aimed at advancing collaborative meditation for neuroimaging research. And today, Saampras will be presenting for real-time neurofeedback methods, practice and applications for meditation training. Welcome, Saampras.
Hey everyone, thanks Beck. So this is going to kind of touch upon some of the basics that one would need to keep in mind while trying to design neurofeedback experiments. And then I'll kind of end with my study, which was on meditation. So how to support meditation training using real-time FMRI neurofeedback. And that part would kind of cover all the initial design practices that I'd be describing at the beginning of the talk. So as Chao has already kind of described what real-time neurofeedback is, I'm not going to show pictures here, but I'm just going to describe it in as clearly as possible. So it's a visual, auditory, or tactile feedback. So tactile in the terms here would be touch. Tactile feedback of one's brain state in real time, which they can then self-regulate and consequently affect behavioral changes. So the idea is to provide feedback of your own brain activity in real time in the form of visual cues or auditory cues or touch, so that you can use that information to then again regulate your own brain activity and so on. So there are many objectives for real-time neurofeedback, but two main objectives include trying to learn and reinforce the mental strategies or skills one is trying to kind of acquire through this training. And the other one would be to produce desirable neuroplastic changes. So in the process of going through a neurofeedback training paradigm, one would ideally focus on executing a particular mental skill or a strategy, and the feedback is meant to guide you to learn to execute it better. And that in turn can produce lasting neurofunctional and neuroplastic changes. Now, in this, as Charles mentioned, in this kind of workshop, we're going to focus on fMRI neurofeedback. But before I go ahead with that, I just wanted to give you a quick overview of a comparison between EEG and fMRI neurofeedback. And this would kind of give you an indirect idea of why we are focusing on fMRI and not EEG. So with EEG, you get very fast data. So the data sampling rates are quite low, quite high in the sense that each data sample comes through very quickly in the span of milliseconds. But the problem is that it does not cover a detailed neuroanatomy of the brain. On the other hand, you've got fMRI, which has got high anatomical precision, so you can get into specific parts of the brain and extract signals from there, which is not possible with EEG. But of course, you lack a bit of temporal resolution. The EEG modality cannot cover the whole brain, especially the deeper parts of the brain, whereas the fMRI covers almost every part of the brain. With EEG, the literature says that it requires weeks to months of neurofeedback training to start to see effects, whereas with fMRI, the literature has shown that you can produce effects beyond placebo in just 2 to 3 brief sessions. In the literature of EEG neurofeedback, there's generally these concerns of poor reliability of the signal, and generally even the placebo control conditions that people have employed tend to be weak. They don't control for all the different possible confounding factors, and hence the results are not always convincing. But then they are affordable and scalable, which is not the case with fMRI. On the other hand, fMRI does have stronger effects. So in the literature, you can see that their outcomes generally tend to go beyond the placebo group, which usually controls for a lot of different confounding factors, which I'll get to in detail. But one of the main disadvantages of fMRI neurofeedback is it's expensive. So the origin of fMRI neurofeedback actually goes back to 1995 when the first real-time fMRI processing pipeline was established. And then in 2005, it culminated in a study which was used to control pain perception. So in this, people saw the C panel. So the C panel is where you have the left and the right. So the right side is where the fire is very high. That's when the signal in the rostral ACC was high. And when the signal was low, the fire was kind of extinguished. So the idea was to get participants to increase the fire and in turn modulate pain perception. So what they did find is they had many control groups doing different parts of activities, but not the exact activity that the main group was doing. What they found was the main group was able to control their target brain region, which in this case is the rostral ACC, which improved over time as they kept practicing. And not only that, they found that people were able to, they reported lesser pain overall. So with the same stimuli, they were given some heat stimulus, but with the same kind of stimulus, only the people in the main group practicing this with the neurofeedback experienced lower intensity of pain, and they were able to kind of control how they perceived pain over time. So which was one of the seminal studies, and it kind of laid groundwork for the field to move forward. And then this is just giving you a brief overview of the literature. So since then, of course, lots of different studies have come up in the field of fMRI neurofeedback. Of course, this is still outdated because the bar ends at 2019, but there have been many, many more studies since then. So a lot of different disorders have been targeted. So it's a very, so this kind of space has been incorporated by a lot of clinicians as well in different parts of the US and Europe to target specific or to explore targeting specific disorders, depression being one of the most commonly targeted disorders. And of course, you've got different kinds of tasks that you can use to target the specific disorder or brain region. So in this case, one of the most common tasks is emotion regulation, which is kind of used in the context of depression. So I'm going to now talk about some of the considerations that one should keep in mind while trying to design fMRI neurofeedback studies. So these are very important. So if you are thinking in the future of planning a study, even a pilot study, you need to consider some of these factors and make decisions before you kind of go on with the study. So the first and foremost would be source of feedback. So as Chao had mentioned, there are many different ways you can source the signal from the brain to provide feedback to the participant. It can be an activation, so it can be just a particular brain region changing its fMRI signal, or it can be connectivity, which is just synchronization of different brain regions. So I'll go into detail after this. The other one's control. So it's very important to control for all the different confounding factors, because otherwise, just the act of putting the participant into a very high-tech environment of neurofeedback and asking them to kind of do a particular task by itself could lead to changes in whatever you were expecting to see. And it may not necessarily be due to the feedback or due to the whole process of training with the feedback. So we want to make sure that we're controlling for all these other factors so that we can isolate whether the outcomes we observe are due to the exact neurofeedback training, or is it something else that, it's not part of the experiment. Feedback characteristics. So whatever the participant sees inside the scanner when they're lying down, there are many different ways you can show the feedback. So it can be complex, continuous, intermittent. Again, I'll get into it. The instructions. So sometimes participants can have very detailed instructions on what they're meant to do. Other times, participants may not exactly have a lot of instructions, but they're still meant to figure out things. Dosage. So a lot of studies have done just one session of fMRI neurofeedback, whereas there's evidence for stronger outcomes with multiple sessions as well. And finally, outcomes. So how do you measure outcomes? So if the participants have gone through an fMRI neurofeedback training, how do you exactly say that we intended to achieve what we achieved with the experiment? So Starting with, so before I go into those details, I just wanted to highlight how neurofeedback training, especially fMRI, has been used in the context of psychiatric disorders and has actually shown meaningful efficacy. So there was a recent meta-analysis which showed that participants tended to learn how to control the target that they were fed back from the brain better over time with more training compared to control group. So the effect size was medium. And then when you remove the feedback, are they still able to control the same region and show same kinds of outcomes? Yes, compared to the control group. These are all evidences from randomized control trials. And that was with a large effect. And finally, how does this translate outside the scanner? Because at the end of the day, you could do all you want inside the scanner, but once the participant steps out into the real world, you need to see if they're able to benefit from what they've gone through. Otherwise, it's very expensive to really have to go through everything without observing any effects. So there you again see that in randomized control trials, behavioral effects were observed with, of course, a smaller effect size. So going to the source of feedback. So this is an important aspect to consider. One of the things you would want to look at is how clinically relevant or functionally relevant the target region that you're considering is. So let's say you want to target addiction, maybe ACC or anterior cingulate cortex is a good region because it has strong implications with addiction. Or it could be something like meditation where posterior cingulate cortex has been implicated. It could be a motor task, so somatomotor regions, motor cortex, etc. So it's important to choose the source based on your literature, based on what we already know about what the task or the condition does into the brain. And the regulation can be either you try to increase the signal, you try to decrease the signal, or you can do both. So it depends on, again, what is the relevance in terms of what you're trying to target. And use of function localizer. So sometimes the literature is not very clear on what regions or what areas you can target. So in that case, you can use something called a function localizer, which is simply getting the participants to go through the experiment, the same experiment that you would do in a neurofeedback setup, but here you're not giving the feedback. So you're just asking them to do the task, and then you're trying to localize which parts of the brain are kind of lighting up during this localizer without the feedback, and then you use that same kind of activated brain to then move on to the neurofeedback training. So you give feedback from that particular region that was activated in the localizer session. You can also use localizers to refine a particular region's activity. So if you know it's ACC, if you know it's PCC, then you could still try to run a localizer, run the task without feedback first, and then see which parts of the PCC or the ACC are being specifically activated, and then you can use that information subsequently for each participant separately. The important thing here to consider is that whatever region you're choosing does not overlap with the general neuroanatomy of neurofeedback control and reward. So just the whole aspect of processing the reward. So because you're getting signals, you're getting, let's say, a thermometer. It goes up, it goes down. So every time it goes up, it's giving you a feeling of reward. It's giving you a feeling of success. And that feeling or that experience itself could have specific brain correlates, which it does. There is meta-analysis on that. So you should ideally try to find brain regions. When you're targeting brain regions, you should find regions that do not necessarily overlap with that whole process of looking at the feedback, controlling it, trying to gain rewards from it. Now, this is control. This is not about controlling the feedback, but rather controlling for confounds. So there are many different confounds: motivation, frustration, neurophysiological specificity. So you ideally want a region or target that's specifically related to what you're trying to modulate rather than a very generic kind of target. Placebo, and of course the perception of success. So there are many different control conditions that have been used in fMRI neurofeedback. I'm not going to go into too much detail into all of these, but just broadly speaking, there's of course the no training control, so which is like the waitlist control, so which is basically one group goes through the neurofeedback training, the other group just does not do anything, but they're given kind of measurements at the beginning and at the end of the study. The other one's called bidirectional regulation. So that one's kind of interesting because one group increases the activity of a particular signal, and the other group decreases the same signal. So you're trying to understand if that region's activity in a particular direction is implicated in a particular outcome. But sometimes it can be controversial, because if you're asking, let's say, a depressed person to increase their rumination, which is what's causing them depression in a way, or which is what's kind of related to depression, then you're not being entirely ethical. So that's kind of one of the issues, can be one of the issues with bidirectional regulation control, but of course with appropriate ethical reviews you can still do that, and there have been studies that have done that. And then of course one of the most common kinds of control groups are the alternative feedback and the sham feedback. So the alternative is where one group receives feedback from, let's say, a particular region, like the posterior cingulate cortex, and the other control group receives feedback from an alternate signal. So it could be an alternate brain region, which is not related to the task, or it could be just be breathing or other artifacts. So you're trying to control for the whole process of receiving feedback and training, just that the exact source that you're providing is kind of different. And then you have got the mental rehearsal group, so which is just a group doing the exact task as a neurofeedback group, but they're not receiving any feedback. So they're just doing the task without any feedback. And of course, the other factors to control for are motion and physiological fluctuations. This is especially difficult in real time because everything's happening so quickly. The the MR images are coming from the scanner, and then you have to quickly process it and then do all these corrections and then provide it to the participant and do it for every volume or every few volumes. So it's important to still consider it. It's not easy. There's only one group in the world currently that does real-time, if you're aware of retro-ICOR, so real-time retro-ICOR regression, which is basically getting the data from these respiration belt and other sensors in real time and then processing it and then giving the feedback. So that's very technically difficult because it involves hacking the scanner a bit, which not every brand of scanner allows. But otherwise, there are other ways to do it, which I'll get to. Finally, feedback characteristics. So here, this, as I mentioned, is the feedback. So this is important because this is what the participant experiences inside the scanner. How is the feedback coming off? So it could be visual, where you're just seeing something on the screen. It could be auditory, which means you're just listening to some modulations of sounds. Or it could even be tactile, where there's something on your finger and then the touch is kind of changed. The vibrations are changed and you can feel that. Temporal contiguity and hemodynamic delay. So this is quite important because if you're aware of this, the signal from the fMRI is actually delayed. So whatever's happening in your brain, it's already happened 5 to 7 seconds earlier, and the signal that you actually measure with the MRI scanner is 5 to 7 seconds later, and that's called the bold hemodynamic delay. So in a real-time situation where you're getting feedback every volume, the actual feedback that you see is actually representing something 5 to 7 seconds earlier. So you have to, as a participant, you have to kind of keep that in mind all the time while you're going through the paradigm, that whatever you're seeing now is actually from the past. But there are some solutions to overcome that. One of the solutions is to not give the feedback every volume, but rather give it after brief intervals. So for example, I receive a feedback now, which represents activity over the past 30 seconds. And then again, I get uninterrupted time for 30 seconds where I do the task. And then after that, again, I get feedback for that 30 seconds. So this way, you're kind of separating the instance of where you see the feedback versus the instance of when you're performing the task. So this not only kind of overcomes the hemodynamic delay issue, but also kind of helps reduce cognitive load. Because otherwise, you're looking at the feedback's fluctuating, and you're also supposed to do something in your head to kind of change the signal. And there's so many things to keep in mind, and it might take longer to kind of train. Of course, there are also kind of advantages to continuous feedback. Because with continuous feedback, the feedback is changing every moment, which means it helps you refine your technique of whatever you're trying to do. It's a more refined, temporally refined way of providing feedback on your performance. So both pros and cons. The other advantage of intermittent or feedback after few volumes or intervals is that there's a low chance that whatever target region you're using is overlapping with the general reward processing areas. Now, complexity as well. So when you're inside the scanner, there's many ways, again, as I said, you can present the feedback. Now, looking specifically at the visual domain, you can have a simple thermometer that goes up or down, or you can have something like that where a person is trying to go up the ladder, so you're trying to increase the activity of your brain region such that the person goes up the ladder quickly, quicker. And at the bottom, you can see it's a VR environment, so it's actually a gaming environment. So the person's kind of going through the gaming environment, and the luminosity or the clarity of, so the top panel is much more visible, the bottom panel is kind of dark. So that's based on the brain activity. So the gaming becomes clearer, easier to play when the feedback is higher, whereas other times it becomes harder to see, and so you're trying to. So there are many ways to do it. And also you can change the threshold. So as you do better, the threshold can increase so that your difficulty levels raised and you can kind of perform better. Now, in terms of instructions, before you go into the scanner, participants can be given instructions on how to do the whole task, and it depends on how well the instructions are kind of gearing them to do the task. But the instructions can be implicit or explicit. So implicit in the sense is that participants go inside the scanner, all they see is the feedback, and they're trying to modulate it. They don't know exactly what strategies they need to use because intentionally it's been left out. This can be useful in, for example, phobia treatments, where you don't want the person to exactly know what they're being treated on, and you don't want them to be exposed to the phobia, but you're inadvertently changing their brain activity related to phobia. On the other hand, explicit is where you tell them everything. So you tell them where the brain signal is coming from, what strategy you need to use, what will happen at the end of it, and so on. And there's also a spectrum. So sometimes you can say a bit of it, you can give them a broad theme, and then participants can kind of explore strategies within that theme and see what works best in terms of modulating that particular signal. And after coming out of the scanner, I think it's important, not a lot of studies do it, but try to understand how the participants performed inside. So what strategies did they use? Was it consistent across participants? Was it related to a specific, was certain strategies successful? Was certain strategies unsuccessful? So it's important to really get at the participant experience to understand what they were doing when the feedback signals were changing. Dosage. So a lot of fMRI neurofeedback studies have focused on doing single doses, so single sessions. One day they come in, they do everything, they go out. But there's a lot of evidence showing that if you do at least 2 or 3 or even 4 sessions. For example, one of the studies, actually 2 studies, did 4 fMRI training sessions, and that led to lasting impact with brain changes that lasted for almost a year, almost 3 months, and behavioral changes that lasted for almost a year, clinical ADHD symptoms. So multiple sessions can help because it helps to kind of consolidate whatever participants figure out in the first session. But on the other hand, can be expensive. Unlike EEG, where you can just put on the headset and keep doing it for like 20, 30 sessions in a month or 2 months, fMRI is very, very difficult because it's extremely expensive. So that's one of the limitations here. But multiple training sessions can still produce lasting impact. In terms of outcomes, so there are 3 main ways to measure outcomes. One is whatever you're targeting, so let's say a particular brain region or particular functional connectivity, how much has it changed from beginning to end? In different ways you can test that. How much has this brain region changed when they were doing something without feedback at the beginning versus when you take away the feedback at the end? So basically you do the task without any feedback at the beginning, then you go through neurofeedback training, and at the end, again, you take away the feedback and ask them to do the same task, and you try to see if what they're doing at the end without the feedback is better than what they're doing at the beginning. And finally, behavioral transfer is pretty much the same as the second one, except that now you're not just measuring brain activity, but you're measuring actual clinical symptoms or behavioral symptoms, which can go on for months or even years if you want to measure the lasting impact of something. So now I'm going to just briefly describe the 7 Tesla fMRI neurofeedback system. So this is one of the first 7 Tesla systems and one of the only active fMRI neurofeedback systems in Australia right now. So you see this is just a schematic of how neurofeedback in fMRI works and how this kind of works in this particular system. So So you've got the scanner, you've got the raw fMRI data coming in from the scanner, which is already reconstructed, goes to the MRI console, and from there, you get the raw fMRI into this computer, which has the real-time fMRI software. So there are many different kinds of software. There's Friend Engine, TurboBrain Voyager, OpenNFT, and so on. But in this particular system, we're using TurboBrain Voyager. And then from there, the MRI images are processed in real time, denoised, corrected, aligned, etc. And then it goes to another computer. Here, this is the computer that kind of then decides what to present to the participant inside the scanner. So it can be visual, it can be auditory, it can be touch. The idea is that this is all in a single network. So communication between these networks is of paramount importance because if there's any delays at any part of the system, then your feedback is going to be delayed and it's not desirable. So from there, it goes then to the participant real-time feedback scores. So currently, the system is at a state where it's been set up. It took years to set up, but once it's set up, it's now plug in and use. So the green boxes that you see here is all you need to kind of work around with to start working with the system. It has a licensed software, and there's also open source template algorithms. So if you ever wanted to kind of come down to Melbourne and use this 7 Tesla fMRI neurofeedback system, you're welcome to do so because things are almost kind of there for you to just tweak around and start working on it. So you don't need to worry about the technical implementation. Now I'm going to talk briefly about the application of all the things that I've discussed. So this is specifically in relation to my study. High precision brain feedback guided meditation training. So I'm not going to talk too much about what meditation is. You may have come across it. I'll just give you a brief overview. So meditation ideally is the process of learning to observe your thoughts and feelings while paying attention to your breathing sensations, which is a basic kind of technique. But it's difficult to do if you guys have tried it. So because generally beginners especially, tend to have low awareness of what's happening inside their head and when it's happening, and to kind of catch it and let it go. So the idea with this is to kind of externalize that process. So the brain feedback kind of helps you understand when you're kind of thinking and when you need to let go and disengage, and how that can then translate to meditation practice. So in relation to whatever I've discussed earlier, I'll go over the study design briefly. So what happened here was participants came in, so before they even come into the experiment, they were given practice. So this constitutes the practice portion of what I spoke about earlier. So they were given meditation practice with audio guides. And then they came in the first day, they did some self-guided meditation and some baseline assessments, which is again behavioral baseline. And then they went through 2 consecutive days of neurofeedback. So this is when they're inside the scanner, they're trying to pay attention to their breathing, and they have this feedback that comes in after every 30 seconds. So they try to meditate for 30 seconds, and at the end of it, there's a feedback showing how focused they were on their breathing. And as you can see at the top there, there's 26 seconds, and then the feedback displays for 10 seconds, which is just a bar that goes up and down, and then it keeps going that way. And there are 2 groups here. So again, we're controlling for things here. Control group was receiving feedback from the brain region of another participant, so a matched participant in the experimental group. So both groups are going through exactly the same paradigm. They're doing the exact same task. The only difference is that one group is receiving feedback from their own posterior cingulate cortex, which is the brain region marked there in yellow. The other group is receiving feedback from another participant's, so it's not their own brain's feedback. So then they went back home and they practiced meditation post this training for 4 sessions at home. And then they came back and did the same thing. So we had some follow-up assessments to understand if participants' awareness improved over time as they learned and went through this kind of paradigm compared to the control group, which is also meditating, by the way. It's just that the feedback is not accurate. And we also wanted to look at emotional measures. So was the control group worse off than the experimental group in being able to regulate their emotions? So it's important to do some sanity checks. So ideally, you would not want to have any group differences in the baseline characteristics, so which was kind of checked. And also, they came out of the scanner and they reported how much they thought the feedback was reflecting their actual signal. So both groups seemed to think that their feedback reflected the actual signal, whereas only one group was getting the real feedback. So this is kind of indicating blinding was successful. So all of these self-report measures were kind of equivalent between groups. And most importantly, none of the participants knew that there was another group in the study. So all participants thought there was only one group. And then this is a few things. So basically, the target signal was correlated with the online and offline preprocessing methods, so which kind of indicates that the real-time system works well. And the control group's posterior cingulate cortex activity was not correlated to their actual activity, which is what we would ideally want. So in terms of the neural findings, there are many ways to observe neural target engagement, which is what I talked about. So here one is directly looking at the region, which is the PCC. There was not much of a difference between the two groups, which is a bummer, but it's not the end of the story, because there are other ways to check target engagement in terms of connectivity. So when you looked at whether the brain activity in the target region changed its relationship to other regions in the brain, it did, and it did in a very relevant way. So the negative correlation between the DLPFC and the PCC was stronger, only in the control group only in the experimental group compared to the control group, and that kind of is relevant to meditation in terms of being able to disengage from mental activity with greater control over it. And most importantly, when we looked at behavioral transfer, which is real-world outcomes, you could see that the experimental group significantly improved their awareness of mental activity in real-world settings. So this is nowhere with the scanner or anything, just going back home, they're using the app and they're meditating, but they actually were more aware compared to the other group. And most importantly, the experimental group experienced greater relief from negative emotional states during that week of neurofeedback bolstered meditation practice. And that improvement in the negative emotional state was actually correlated with the emotional well-being. So, the emotional well-being was correlated with the brain change that was observed in the previous slide. So it's a very strong kind of brain behavior correlation as well. So that's kind of just giving you an idea of what that study is and also how it relates back to the initial components of design characteristics that were discussed. And this is a broad team with many different disciplines. I would like to especially acknowledge Andrew Zaleski because he was kind of the primary supervisor of this whole study and the establishment of the neurofeedback system in the 7 Tesla scanner. And finally, it's done, but if you want, please scan this because this contains some resources which you can go through in detail. It's a handout, and it's also a practical exercise. So if you have MATLAB, you can do everything, and you can actually observe neurofeedback changes, and you can code stuff in real time. So everything is kind of really detailed in it. And also, if you don't have MATLAB, the instructions on how to install it and how to install Psych Toolbox. So it gives you the whole package, and you can do it in your own time. It's a complete hands-on practical guide. Yeah, that's about it.